Pluto sits nearly 4 billion miles from the Sun, locked in permanent, brutal cold. And yet, when James Webb finally turned its instruments toward it, the tiny world was doing something no atmosphere anywhere else in our solar system does, not reflecting heat, not simply trapping it, the way every other planetary atmosphere we've ever studied behaves. Something closer to the opposite, actively pushing heat away, almost like the planet had built its own thermostat. Nobody predicted this would be confirmed so clearly, and the person whose theory it finally proved right had spent years being told he was probably wrong. Here's what Webb actually found in Pluto's thin, fragile atmosphere, why it doesn't match anything else we know, and why one very patient scientist just got the vindication of his career. To understand why this discovery mattered so much, you need to go back nearly a decade to a prediction almost nobody outside a small circle of researchers took seriously at the time. Back in 2017, a planetary scientist proposed something that sounded almost backwards. Most atmospheres regulate their temperature the way a greenhouse does. Gases trap heat, and the planet warms in response. He suggested Pluto's atmosphere might work in the opposite direction entirely, with a high-altitude haze layer actively cooling the planet by radiating heat straight back out into space. It was a bold claim about a world we barely understood. At the time, we'd only had one close look at Pluto ever, from a spacecraft flyby a couple of years earlier, and nothing in that data could confirm or deny a theory this specific. The idea required an instrument sensitive enough to detect faint mid-infrared emissions coming from an object this small, this cold, and this far away, technology that simply didn't exist yet when the prediction was first published. So the theory sat there, mostly unproven, for years. Interesting on paper, untestable in practice. Exactly the kind of idea that quietly fades from the conversation while everyone waits for better tools. Then James Webb launched, carrying an instrument built specifically to see in exactly the wavelength range this decade-old prediction depended on. Even with Webb's power, Pluto still presented a genuine problem. It doesn't orbit alone. Its largest moon, Charon, circles so close that from Webb's vantage point, the heat signatures of both worlds blur together, making it nearly impossible to know which faint glow belonged to which body. Researchers had to carefully separate those two overlapping signals, isolating Pluto's own thermal emission from Charon's, before they could even begin testing the original theory. It took patient, careful work, comparing measurements taken at different wavelengths before a clean signal for Pluto alone finally emerged. When it did, the data lined up almost perfectly with the decade-old prediction. Pluto's haze really was behaving like a thermostat, radiating heat outward with striking efficiency, keeping the dwarf planet's atmosphere far colder than a simple greenhouse model would ever predict. It's a phenomenon that, as far as anyone can tell, doesn't happen anywhere else in the solar system in quite this way. Every other atmosphere we've closely studied traps heat to some degree. Pluto's haze appears to be doing the opposite, actively working to cool the planet down. Here's what makes this finding more than just a neat confirmation of an old theory. It reframes how we should think about Pluto's entire atmosphere. That thin haze isn't just sitting there passively. It's made of tiny particles formed when sunlight breaks apart methane and nitrogen molecules high above Pluto's surface. And those particles turn out to be remarkably efficient at absorbing sunlight and immediately re-emitting it as heat straight back into space before it can ever warm the lower atmosphere. That process gives Pluto something close to climate control on a world with barely any atmosphere at all, a few millionths of Earth's atmospheric pressure, thin enough that it would have seemed almost too fragile to have any real climate system whatsoever. And Webb didn't stop at confirming the thermostat effect. The same observations revealed a genuinely strange, previously unconfirmed interaction between Pluto and Charon, evidence that material is slowly being pulled directly off Pluto's atmosphere and deposited onto its moon's surface. Nowhere else in our solar system does a planet's atmosphere feed material to its own moon quite like this. It's a relationship that only makes sense given how unusually close together and how unusually similar in size Pluto and Charon actually are compared to every other planet-moon pair we've studied. Put together, these two findings paint Pluto as a genuinely unique case among every atmosphere we've ever studied up close, cooling itself with its own haze, while quietly losing pieces of that same atmosphere to the moon, orbiting practically on top of it. It would be easy to file this away as a curiosity limited to one small, distant world, but researchers studying Pluto's atmosphere think it might actually tell us something about much bigger questions closer to home. Pluto's atmosphere, thin as it is built almost entirely from nitrogen and simple hydrocarbon chemistry, remarkably similar in basic composition to what scientists believe Earth's own atmosphere looked like billions of years ago, long before oxygen ever built up and made complex life possible. Understanding exactly how a haze-driven system like Pluto's regulates temperature could offer real insight into the kind of atmospheric chemistry that existed on early Earth, and potentially on other worlds, with similarly thin nitrogen-rich atmospheres that we're only beginning to study around distant stars. It also raises fresh questions about just how differently very small worlds can behave, compared to the planets that usually dominate our models. Pluto isn't a large planet with a thick, well-mixed atmosphere. It's a small, cold body where a handful of unusual physical processes can end up controlling its entire climate almost by themselves. The combination, small size, extreme cold, and an active haze layer working overtime, might turn out to be a genuinely distinct category of atmosphere, one we've simply never had the tools to properly study until now. Researchers are already planning follow-up observations, hoping to track how Pluto's haze and atmosphere shift over the dwarf planet's extremely long 248-year orbit around the Sun, as different regions slowly move in and out of direct sunlight. There's particular interest in whether the thermostat effect strengthens or weakens as Pluto continues moving further from the Sun after its closest approach decades ago, and whether the slow transfer of atmosphere onto Charon changes pace as conditions shift. Every new observation adds another data point to a theory that spent nearly a decade waiting for the right instrument to finally test it. And now that it has one, Pluto's atmosphere is turning out to be stranger and more actively dynamic than almost anyone expected from a world this small and this cold. A theory almost nobody outside a small research community took seriously for the better part of a decade just got confirmed by one of the most powerful telescopes humanity has ever built. Proof that even the coldest, quietest corner of our solar system can still surprise the people who've spent their entire careers studying it. Pluto isn't just a frozen, inert leftover from the early solar system. It's actively managing its own temperature and slowly feeding its own atmosphere to the moon orbiting beside it, in a process that doesn't play out quite the same way anywhere else we've looked. If you want to see what Webb finds the next time it turns back toward Pluto, and whether that haze-driven thermostat behaves any differently as the dwarf planet drifts further from the Sun, that's exactly what I'll be covering the moment new data comes in. Subscribe so you don't miss it. And before you go, tell me in the comments, what other small, boring world in our solar system do you think is hiding a genuine surprise like this one? I'll pin the most interesting answer